Okay, welcome to Geometry Project number 16. 16? Oh, it's actually Geometry Project 17 because I didn't do a video last night. So, welcome to Geometry Project 17. Sorry if my energy's a little low today, kind of a rough day at work. Thatwe do have a really wonderful little theorem to work through tonight, and maybe that'll get my energy up a little bit. This is section 2.8 of Geometry Revisited, and the theorem is called the butterfly theorem. And it goes a little something like this. Take any chord in a circle, we'll call that PQ, and we'll call the midpoint of that chord M. Now, draw any other two chords passing through M, AB and CD. So here's AB, here's CD, nothing special about AB and CD, any chords passing through the midpoint of PQ. Then, what we have, if you draw AD and BC, which I've drawn here, and they intersect the segment PQ at X and Y, then M is also the midpoint of XY. And you can sort of see the butterfly in the picture. That's a pretty amazing theorem. The book makes kind of a fun little comment, and the comment is that their proof, although not the simplest, is actually easy to remember. And sure enough, I remember this from high school. This was probably the first very difficult geometry proof that I spent some time working through and actually came to understand. So I'm happy to be saying this again. Like I said, kind of a rough day at work. Nice to get back into this. So let me turn the camera off for a second and redraw the little picture that's going to help us through the proof. And all right, let me do that right now. The new picture. It looks a little awkward. I'm trying to follow the notation conventions in the book, and just for simplicity, they label as a distance A the distance from P to M, which is also the same as from M to Q, so that's why my little arrows go there. Alright, so all we're going to do to prove, now remember what we're trying to prove in this theorem, that x equals y. That's what we're trying to prove. So does x equal y? Well, the very first thing to notice is that we have a lot of similar triangles lying around. And what I've done is I've drawn the perpendicular from x down to AM, call that x1. Call the perpendicular from x down to DM, x2. Drawn the perpendicular from y down to CM, I've called that y2. And the perpendicular from y down to BM, I've called that y1. So you'll notice that this angle is equal to this angle, and this angle here is equal to this angle. And that tells us that the right triangles MX, x1, for lack of a better word, this triangle here, is similar to this triangle here, MYY1, where you've got a right angle there. And so that tells us that x over y, the sides of those right triangles, the x and y are the hypotenuse, equals x1 over y1. So that's fact number one. Okay? So hopefully you can see that x over y equals x1 over y1. Now, from these other triangles, we have two other similar triangles, x down to x2 up to m, and y down to y2 down to m. And that tells us that x over y equals x2 over y2. Also, exact same reasoning. Okay, so x over y equals x1 over y1, and x over y equals x2 over y2. Now, we have several other pairs of similar triangles. Let me draw these ones in red just so they're a little easier to see. You notice that the angle here at A inside the circle cuts off this arc when I extend it down here. And it's also the exact same arc that's cut off by this angle C. And that tells us that this little tiny red triangle here is similar to this red triangle here. Well, that tells us that x1 over y2, I want to do it that way? Yeah, I guess I do. x1 over y2, so the ratios of this side to this side here, x1 to y2, is the same as the ratio from ax to cy. Okay? x1 over y2 equals ax over cy. And finally, by the exact same reasoning, this angle here at D cuts off this arc, which is the same arc cut off by the angle here at B. So that tells us that this little triangle here is similar to this little triangle here. BYY1 is similar to DXX2. And that tells us that x2, this distance, over y1 equals dx over by. So these are my four little relations, and we're going to have, there's a very interesting little algebra trick that you do. Let me see. Sorry, I got to peek in the camera, see how much room I have on the screen here. Ooh, not very much. Let me see if I can't give myself a little more room by writing a little more carefully. So turn the camera off for just a second and rewrite this. Okay, hopefully that's a little better. Okay, now we have some very clever algebra. So remember, we're trying to see if x, this distance here, x equals this distance, y. And we've found these four relations, 1, 2, 3, 4, just by peeking around at similar triangles inside our little butterfly. But that tells us just from algebra that if we take x over y times x over y, which equals x squared over y squared, this equals x1 over y1 times x2 over y2. This is all just algebra, this proof. x1, x2 over y1, y2. And now we can play a clever little switching around y2 and y1, because here we have x1 over y2 and here we have x2 over y1. So this equals x1, x2 over y2, y1. But that's just x1 over y2 times x2 over y1, which happens to equal ax times dx over cy times by. Okay? So, again, this is all just algebra. But what is ax times dx? Well, ax times dx, let me pick a different color, sorry about that. How about orange? Ax times dx is just equal, by our theorem about intersecting chords, equal to px times xq. So, back to purple. So this equals px times xq divided by exactly the same reasoning, cy times by. Cy times by equals, what should I call it, qy times yp. Okay, so hopefully you see those intersecting chords. Sorry, having trouble with the marker. Okay, and how am I doing on room? Oop, just about out of room. Now you remember I called the length from P to M A, and this distance from M to X we were just calling X. Well, Px is just A minus X then, and where shall I write this? Px, let me just go, the only room I have is actually inside the circle. It's probably bad form, but Px is just the distance A to M, subtracting away X, so that's A minus X. And then X to Q, by the same reasoning, is A plus X. Similarly, Q to Y is just A minus Y, and Y to P is A plus Y. So which did I write? I wrote QY first, so this is A minus Y, A plus Y. Well, this all multiplies out to be A squared minus X squared over a squared minus y squared. And remember, we're just assuming from the beginning that this is equal to x squared over y squared. Okay. The only way, well, there's a couple things. There's a neat algebra trick that if this is true, if you multiply it out, you find that this is, what am I trying to say? Oh shoot, let me just show you the nice little algebra trick. Sorry, I'm going to have to erase. If A over B equals C over D, then this also equals C minus A over D minus B. Okay, so if two ratios are equal, you can subtract the numerator and denominator from one of them and you get the same ratio, as long as none of these things are zero, obviously. Well, look at this. And similarly, you could add them. I have two things that are equal, so I'm just going to add x squared over y squared to this side, which tells me that this then becomes a squared over a squared, which equals 1. But remember, this is equal to x squared over y squared. So it's just a very clever algebra trick, followed, starting with some similar triangles, dropping your really nice perpendiculars, and then the algebra just flows through. It's a very nice result. In fact, it's gotten me a little bit out of the mental funk I've been in all day. So very happy to show this butterfly theorem and how it works. It's a beautiful theorem. I think it goes back to Greek geometry, although I'm not totally sure about that. So thank you for watching. I hope you enjoyed this lecture about the butterfly theorem.